Hello guys, nice to see you.
Good morning.
Hi.
Okay,
Hi.
good afternoon.
Good afternoon.
Good afternoon.
Yeah, hi, nice to see you.
Hello.
Hi. Hello.
Hello.
So how things are going on, guys? Everything is good? Any problems, issues?
No problems, thanks.
That is good. So first I would like to tell you that okay, is midterm going to be hard? I believe not. Piece of cake. So need to prepare, but it has to be some. It has to have some level of complexity, because if it's very simple, you will all solve all problems, get A's, and that's not how it's supposed to be. Only few of you should get A's. So we will use long kappa, the same as homework. So there will be access via long kappa to your assignment. There will be some problems assigned to you, and you will have some limited time to submit your answers. How you can properly prepare for midterms. You know which topics are going to be covered by which midterm, like those which were prior to midterm. And first you need to understand physics concepts, which make the basement of these chapters. And then practice in applying them to solving different problems. Keep in mind that have somewhere next to you some table of integrals and derivatives that may also help. I mean, it's always accessible, but maybe in some stressful moment it will take some time for you to find it, and better have it next to you. And you are allowed to use any sources of information, textbook also. So you don't need to remember all equations and concepts, but understand them. That is the key, because then you will find what is. You can put 9.81 for G. I think that will be in the scope of most problems provided by long kappa, quite good number. Okay, so first I would like to tell you that unfortunately our instructor Scar got sick, and for some time he will be not available because of obvious reasons. And so those students who are in his sections for recitations, so first of all, I believe he sent you this link already. Yeah, so this is the link where you can watch some detailed consideration of different problem solutions related to our course. So that definitely will be very helpful. And in addition, of course, like specifically during this time when he is not able to work with you on recitations, we can dedicate some time during our discussions for some physics concepts and also of problems you don't understand. So that was not my plan. Of course, I was planning to focus on physics specifically and provide you with some derivations and explanations during our discussions. However, taking into account these circumstances, we can also discuss your current questions related to some interesting problems on our meetings here, which is according to the concept of this flipped class. Technically, it's supposed to be like that. We should just discuss your questions on the textbook. And however, I believe that when I have some initiative in terms of providing you with new concepts and their explanation, that works based on my experience with previous groups, works better in general. So we have, yeah, sure, you can interrupt me and ask question.
Good afternoon, Professor. I have a
Hi.
question about lone kappa. So as a first homework question, I believe it was about superposition of forces. I entered the correct answer, but I did not have a correct number of significant figures. So it should have been 3.00 and 5.00, but I entered just 3 and just 5. It returned me as it returned that as a mistake and the wrong answer in the end. Can you somehow, I don't know, fix that or something?
Okay, so didn't it tell you that not enough significant numbers, like figures of in an answer, and immediately claim that this is the wrong answer?
No, it didn't somehow.
Interesting. Well, so this is, as I understand, for the first homework for week number 2.
It's for the week number 3, that one graded homework. Yes.
Okay. Then in this case, when you have some issues like this, but please for future, don't forget about this. What you should, as we, excuse me, please. As we discussed previously, you make the screenshot of the problem, your solution, step by step, and also when the screenshot of this not accepted answer by lone kappa, then all these screenshots and photos of your step by step solution you send to me. And we will take this into consideration.
Okay, thank you very much.
You're welcome. Okay, good. So I guess I don't know, unfortunately, how long our instructor, like recitation instructor, will be on sick leave. But on this, during this time, we definitely can discuss some questions related to problems. Once you have any questions, you let me know and we can do that.
Sorry, Professor, I have a question.
Yeah,
So
sure.
if there are like 2 parts in a problem, and one of them is incorrect and another is correct, so half of the problem or half of the score will not be given, right? Or it should be given?
So there were 2 questions.
No, one question with 2 parts, like A, B.
Oh, okay. One with question A and B. That's good question. I will double check with this. I cannot answer exactly. Usually, yeah, it's difficult to answer right now. I will ask and let you know. Maybe, yeah, maybe you can also email me. So email me, please, so I will recall me to ask, because I think that also you can ask it for our Long Kappa administrator, because that is really depends which features of Long Kappa are activated there, how it works, like this algorithm of its functioning. But I can also ask this. A and B. And it was for one part, it was accepted by Long Kappa, and for another, no. Correct?
Yes.
Okay. Yeah, you are welcome to ask.
Maybe we could go through homework problems for this week all together.
Oh, I believe that you can find similar or even these problems on this YouTube channel from Askar. But definitely we can discuss like some of them, like the most interesting, which you consider are most difficult, because let us focus on the most interesting problems, so we have some time to also discuss the new topics we need to during this week. We will need to introduce work, mechanical work, kinetic energy, and potential energy. So if you have some specific problem to ask, we can definitely discuss. So here is. So do you require notes? I mean, so notes, if you don't have them already, but what do you mean? Will you require notes that we used during the exam for calculations? I mean, if you complain on some problem and claim that it was either problem issue or Long Kappa issue, then we will definitely need your step-by-step solutions. But other from that, no, we will not require your calculations. We require your correct answers submitted to Long Kappa. Okay, another question. Week number 2, I have wrong answer with standard deviation. Oh, okay. So I think in order to save time with this, so there are like simple like standard deviation, also corrected standard deviation. The point is that that was some misunderstanding at the beginning for week number 2. In any way, it's not graded. It doesn't affect on your final grade. Since we don't have detailed chapters dedicated to this topic of standard deviations, that not supposed to be into assignments, this topic. And of course, it will not be in the midterms and final exams. So don't worry about that. And it's, yeah, the obvious reason for that it's not covered by the textbook. And yeah, textbook is the same for everyone. One more question. Yeah, Amira.
Oh no, sorry, I forgot to.
Ah, okay. Never mind. It is allowed, but usually, so is the question if it's allowed to type like 56.5 or 5.65 10 to the power of 1. check for requirements in long kappa. And maybe, by the way, this assignment, which was made for week number 2, it remains active until the end of semester. And we intentionally made it open until end of semester. And then now if you go there and try to submit your answers, you will see the answer, like response from long kappa, either it's accepted or not immediately. So that is made for you to have an option to double check your suggestions according to long kappa. So you're welcome to try this. That should be available for you. So you can try both, but I believe there is no need to go for 10 to power when you have small numbers. I mean, that is already usually applied when you deal with large numbers, so it just makes it more convenient. So I would recommend just stick to 56.5 and don't invent anything with that. But yeah, keep in mind that this option is available, and don't miss it. You could double check something and get the response immediately, so it will be quite convenient, I hope. Okay, guys, so then we can proceed with the introduction of mechanical work, and on the way, if we have any questions, we can discuss. And for instance, if you have some specific problems you want to discuss, either we can ask me on the way, or another option, maybe to make it more structured. If you have some specific problem, can maybe submit it to my email. Let's see how it works. Maybe it's better because let's see how many I get responses from you, and I will try to address those problems which are the most relevant for, like, has broader impact and could be more helpful to more of you guys. So there's a question. Include chapter 1.6, the midterm. Let's double check. So where is our manual? Let's check what is there. Folder for students, manual. Where are they? Midterm. Midterm this Saturday, and application of Newton's laws. Yeah. So this chapter 7 and 8, which we will consider during this week, since it's the week before the midterm, it will not be included in the midterm. So it's from 1 to 6, including 6, means application of Newton's laws. However, let us proceed with our new topic. Let me change the camera. And mechanical work. So obviously, if we have some body and apply the same force in magnitude in different directions, let's say like this, it will have different impact on the behavior of this body. So in first case, it would tend to slide, depends on the force and magnitude of the force, and also on the friction between the surface and this body. Like for the second example, it will just press the body towards the surface, and there's no option to cause any sliding. So the effect of the force on the body depends on its orientation with respect to the body and surface on which it resides. For instance, taking into account this particular example. So means this effect should be somehow quantified, taking into account this orientation. So let us now consider a body with some force applied to it. So this is axis X. Then under the effect of this force, this body move to a new position. So the distance between these two positions we will call delta R, like change of position vector, which is displacement. And here we have some angle, let's call it alpha. So by definition, mechanical work, which denoted as W, capital W, is equal to dot product of force vector and resulted displacement vector because of this acting of this force. So we know from previous discussions, like a bit and mention that to recall your information about dot product, that the result of dot product is a scalar. It's not a vector, so work is not a vector. And in order to get its like value, we need to multiply magnitude of force vector, magnitude of displacement vector times cosinus, cosinus alpha, which is the angle between the direction of force vector and displacement vector. So the units for mechanical work are from here we already see this, it's Newton times meter. Newton times meter. And there is introduced additional unit which specifically describes work done by mechanical force. It's joule. So Newton times meter is joule. So this is units of mechanical work. Now we need to decide also when work will be positive and negative. Apparently that would be. And again, just short comment here. We obviously need some displacement, which is caused by the exerted force. If force is applied, but there is no displacement of the body, for instance, if force applied perpendicularly and body doesn't move anywhere, means that work is equal to 0 because delta R, the change of the position vector or the displacement vector, will be equal to 0. So now with respect to the sign, if we have some body and there is some force which causes displacement, for instance, and displacement vector delta R is pointed in the same direction as applied force, then work is considered to be positive. So when they coincide, work is positive. However, could be another situation when, for instance, we have some body which already moves with certain frequency, certain velocity, and then we start to exert some force which slows down this body. However, it's slowing down. However, displacement is still in the direction of this velocity. So this is velocity. And that means that delta R pointed also to the right. So now we have different orientation of displacement and force applied to this body. So mechanical work of this force in this particular case will be negative. So this should be taken into account. So far, we consider that force is constant. We don't change force. We have some displacement caused by this force, and then these equations can easily give us the answer what is the mechanical work done by this force. However, that's not the case always, and force can be a function of position, for instance. As if we consider this axis x, force can be a function of x. In this case, we should address this because force is changing and from position to position, and obviously work will not be the same. So graphically, we can consider something like this. Here is our position. Here is the force exerted on this body. And that could be some function, f versus x. So in this case, for instance, we are interested which work will be done by this position-dependent force by moving our body from position x1 to position x2. So for this purpose, what we can do, we can consider some narrow ranges of delta x. So something like this. So it will be x, and here will be x plus delta x. Delta x is quite small, and therefore we can consider that within this narrow range of position, f remains constant. Then within this narrow range delta x, the work done by this force can be easily calculated by applying this rule for constant force. However, that is only true at this very small interval. So in order to get work done by this variable force f as a function of x, or large displacement from x1 to x2, we need to integrate, obviously. So consider many of these small intervals, and then sum up work done by force at each of these small intervals in order to get the total work done. So that is like mathematically carried out as integration. So work will be equal to x1 from x2 f x dx. So that gives us the answer how we would get the work done by a variable force. However, so far, as you may already notice, we deal with one axis, x, so it's one-dimensional motion. And obviously, we also need to be capable of dealing with multi-dimensional motion. In particular, first, the easiest example, two-dimensional motion. So let us go to another slide. And here we can apply the same concept. We need to integrate if we have some variable force, but in this case, it is force which depends on position vector. And position vector is given in this two-dimensional space. So the work done by such force in general will be written as sum of scalar products, like integral of sum of scalar products for all directions from I1 to n, which is in our case will be 2 for two-dimensional. And we have Fi as a function of position vector times dr change of the position vector. To make it more clear, let us show this. So we can express this function of force as a on position vector as fx as a function of x times I unit vector plus fy as a function of y times j unit vector. And also we can express the change of position vector dr, which is dx times I unit vector plus dy times j unit vector. Okay, so now we have this, and we know that integral of the sum is equal to sum of integrals. So we can write, in this particular case for two-dimensional motion, that work done by variable force, you can write it like this. So it will be moving from point 1 to point 2, so integration from going from point 1 to point 2 in two-dimensional space. Then we have this force as a function of unit position vector times dr vector. And we can express it now in components, like two components, two integrals. It will be integral from position 1 to position 2 when we consider x direction. So it will be fx as a function of x times I unit vector times dx times I unit vector, because these both are vectors. You see, here is vector and here is vector. And here we have also two vectors, but they are components which are aligned along axis x in this case. And we have this dot product between two vectors. So then we have another component, which is along axis y. We integrate from position 1 to position 2. And here we have fy as a function of y times j unit vector times dy times j unit vector. So this is the way how we address, and here is obviously this point product of these two vectors. How we address work done by not constant force in two-dimensional space. So is it clear with this? Any questions?
I ask,
Yeah, sure.
how did we get 2 and 1? From what point?
1 and 2, you mean this integration limits?
Yes.
So it's not just 1 and 2, maybe it's a bit confusing. So let us write here 0.1, 0.2
Mhm.
in two-dimensional space. So we kind of move from 0.1 to 0.2. Initial and final position of the body, which moves under effect of this force F, which also depends on position, vector R. And that's the way how we calculate the work done. So thank you for comment. Probably it was not so obvious, but this is initial and final position of the body, denoted as 0.1 where it starts and 0.2 where it stops. Okay, so probably we can consider some example of work done by force. So let us maybe go to another slide and let us consider some string and a body attached to this string. So let's have string, body, and let it be. So there's some mass obviously of this body, but in this particular case, it doesn't matter. So it's equilibrium condition. So position x equals 0. It's not moving anywhere. It's in equilibrium. So then what we do, we apply some force F to this system and compress the string. So here, string is already compressed. And this is, let's say we have x is x. This is x equals 0, and this is x. Let's just say that it's minus x, some negative position, like coordinate of which defines position of this body after we push this body with the force F to the left. Now imagine that we let this system to move freely. So we eliminate force F suddenly from this body, and it starts to move backwards. So it moves because of some force, string force, which could be calculated as minus kx. So it is in opposite direction to the displacement of the body. And k is the string coefficient, which defines how strong this string is and how much force, string force it exerts on the body for certain displacement of the body, like certain compression of the string. So now we consider, keep in mind, we consider force which is exerted from the side of the string on the body. So inside this system, not external force. So that is the force with which string will act on the body when it released and can freely move backwards to its initial position. So now work done by the string will be considered, and again we see that this F is a function of x, so it changes with position, so it's not constant force. That's why we need to keep this in mind. So in this case, we need to apply integration from initial position, which is minus x, to let us consider work done by a string force until this body comes back to initial position x equals 0. So here we can put 0. And here we have minus kx, which is string force, times dx. So if we integrate this, we will get minus k times x squared divided by 2 from minus x to 0. And this is equal, so we can write here, let's put this minus outside the parentheses. Here will be a 0 because we have substitute 0 instead of x. It will be 0 minus kx squared divided by 2. So in this case, we have minus and minus, so it will be plus k times x squared divided by 2. So this is work done by the string force. This is string force direction, which is pointed towards the same in the same direction as the displacement of this body, because it moves under this force Fs from left to right, from position minus x to position x is equal to 0. So we see that directions of these force and displacement vectors, they coincide, and means that we have work done by string force equal to kx squared divided by 2, and this is larger than 0. Okay, so let us go one step further and consider what will happen if, because we know that if we don't have any friction, like any dissipation of energy, which we will discuss a bit more in details in the future, this body will gain some velocity vector and will continue to move further. So what we will have eventually, that the string will be stretched and this body will be located at some coordinate, some positive coordinate x. In this case, we have the same rule applied for the string force. So here, Fs, it's equal to minus kx. However, our initial and final point will change. Now what we want to calculate, let us calculate from, so we translate this intermediate condition when it's at 0 here, and we want to calculate work done by the string force, which will be now pointed in the opposite direction. By moving the body from position x equals 0 to new position x larger than like some positive x. So in this case, we integrate, again, we get this work done by string force will be, let's mark it as going from 0 to some positive x, will be equal to integral from 0 to x. So we had before from minus x to 0. Now it's from 0 to x. Again, this minus k times x times dx. So we get minus kx squared divided by 2 from 0 to x. And this is equal to, let's keep this minus out of parentheses, kx squared divided by 2 minus 0. So here we will end up with minus kx x squared divided by 2. So this work is smaller than 0. And we see that this is the direction of the string force, which is pointed from right to left. And the body, the displacement vector, it was moving from left to right. So there is a different direction of force and displacement vectors. And that's why our resultant work of this position-dependent force, which in this case is string force, is negative at this interval between x is equal to 0 and positive x. So now, if we take a look and consider work done by string force from moving this body from initial position minus x to final position x. Here is our string force d x. That will be equal to the sum of work done by moving from minus x to 0 and from 0 to x. So it will be this work as minus x to 0, which we calculated, and also we calculated ws as we move from 0 to x. And that will be, if you remember, we had kx squared divided by 2 minus kx squared divided by 2. So the work, like net work, will be equal to 0. So net work is done from moving from minus x to x is equal to 0 because in absolute values, minus x is equal to x. So at half of this interval, work was positive, at half was negative, because the string force changes its direction with respect of the displacement vector, and eventually we get some net work done equals 0. So if now let us write finally general case, this work of the string, if we have some random position x1 and random like initial position x1 and random final position x2, we need to obviously integrate from this initial to final position. It will be minus kx squared divided by 2 from x1 to x2. And that will give us the option to calculate. So taking into account this minus also, it will be k times x1 squared divided by 2 minus kx2 squared divided by 2. Okay, so that will give us this final equation, how you can calculate when we have just some random initial and final positions of the body, which moves under the spring force. Okay, with this, I think it's everything what I wanted to tell you about mechanical work. And further, we will proceed with introduction of kinetic and potential energy. Okay, any questions? I think should be quite clear with this. And yeah, then thank you very much for your attention. Have a good evening. Take care and hope to see you on Wednesday.
Thank you. Goodbye.
Bye-bye.
Thank you. Goodbye.
Goodbye. Thank you.
Bye.